Ready? Okay, so we're on 1B.6, polynomial functions and in behavior, okay? For this, we're going to just reiterate things that we already know about our functions and behaviors, correct? Like we already know that polynomials only have 4 dance moves, correct? Okay, so that's what we're going to quickly kind of focus on. So up first, our in behavior, okay? The in behavior function describes a function, how a function behaves, and it moves infinitely to the right and left. So as it goes forever to the right, forever to the left, what is that function doing? Okay. In other words, the in behavior is what happens to the values of your f of x. Okay. What are your y values doing? It's not that x's are telling us where we're going. Y is why we're there. So what are your y values doing as you go forever to the left and forever to the right is what you're asking yourself. Okay. Or not. I didn't want to write anyway. It was a trick. There we go. So f of x is your y, right? So we previously talked about in Algebra 2, pre-Algebra 2, about writing that as a limit. Do y'all remember? We wrote as a sentence, as x goes to positive infinity, this is what happens. So in Algebra 2, we wrote it like this. As the x values decrease or whatever without bound, we wrote it as x. Oh, I forgot this is my no writing zone. As x goes to positive infinity, blah, 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 blah. Do y'all remember writing that sentence when we described? Okay. Instead of writing that sentence, what we're going to be using is limit notation. Limit notation, remember, mathematicians are ultimately lazy, right? We want to be able to use the least amount of characters when we're trying to explain ourselves. So they're like, instead of writing all this hoopla, we're going to just write it like this. Okay, it's called limit notation. So as the limit, as x goes to negative infinity, f of x is doing what? Meaning f of x equals blah, blah, blah. Does that make sense? Okay. And so we're just taking what we already know and we're just now lazily writing it. Okay. Is how I viewed it as a student and how I'm going to keep telling you to view it as a student as well. Your right in behavior is your limit as x goes to positive infinity. Sometimes you'll see the positive symbol on the infinity and sometimes you won't. Is it really necessary? No. It's only necessary to label it when it is negative. Capiche? All right. So let's practice writing in limit notation. All right. So here we have two polynomial functions. Agree? These two polynomial functions, we know how they have their dance moves. The first one, it is on the left side, we're going towards positive infinity. Agree? So on the left side, we're heading towards positive infinity. And on the right side, we're heading towards negative infinity. When I say we, I'm talking about our y values, correct? So all the y values on this side are positive. All the y values on this side are heading towards negative. We're describing the y, okay? So when you're writing it verbally, that's where you're writing your left behavior verbally. So as x goes to negative infinity, y goes to positive infinity. I can't really write in this space, but that's the best it's going to get for me. So that is it in words. In limit notation, we're writing it as limit as x goes to negative infinity, f of x equals positive infinity. Isn't that way more faster? Isn't that way better? Is it lazy? A little bit, but it's still conveying the same message, right? Okay, so we're going to do the same thing on the right-hand side. So on the right side, we're describing what happens. So on the right side, we're saying as x goes to positive infinity, our y goes to negative infinity, essentially, right? That's the layman's term. Is that the exact mathematical way of writing it? No, because I'm supposed to write the word approaches and all these things. But you see how small my space is? I can't write those words. So we're going to write in simple words. So therefore, the limit as x goes to positive infinity, f of x is going to negative infinity. All right, so you should have the gist of it. So I would like for you to take a moment and you're going to do the other one. Is that fair enough? All right. Okay. So on this side, we have an even function, right? It's an even polynomial. How do I know it's even again? Both of my end behaviors are doing the same thing, right? They're doing even behaviors, okay? So as x's are going to negative infinity, my y's are going to positive infinity, and vice versa. Would it be annoying if I didn't write the verbal? Is it okay if I don't? Is, is it okay? All right, so we're going to write it. Limit as x goes to negative infinity, f of x equals positive infinity. The limit as x goes to positive infinity, f of x equals positive infinity. Limit notation. We did it. Yes. All right. Again, if you want to be very specific, could you put the plus sign on the positive? Yes. But is it necessary? Not completely. All right. It's just a guarantee that you understand. All right. So what I want you to do here is to make sure that you have an understanding of what the limit notation has. Remember how on your practice you created your own polynomials, right? You had to create your own polynomial. Essentially, you're going to do the same thing here. You're going to create your own polynomials, making sure that the limits apply. Does that make sense? So yours may not be the same as the person next to you, and that's perfectly fine. But you do need to make sure that the following limit rules apply. Got it? All right, and go. Here we go. So this is me going to be professional here. I'm saying it the full way. So this limit right here, the first one, our first limit says, this is the official way, as your x's increase without bound to the left, your function is approaching negative infinity. That's what we're supposed to say. So yay, I did it. But we understand what's happening here, right? So when I have this function on the left-hand side, I need to, whatever I'm doing, I need to be going down, correct? Because it's heading towards negative infinity. Also on the right-hand side, I need to also be going down. So they both need to be going down because they're doing the same behavior. I know I have to create what type of polynomial? An even degree polynomial, right? It could have been something as simple as a quadratic. Is that a pretty quadratic? Nope. But that's why it erased itself, because it said this is terrible, ma'am. I'll make a, yep. Thank you. Thank you. Came straight from my imagination. But did I satisfy the limit? Yes. Okay. On this one, it says the limit as x decreases without bound, g of x is approaching what? Negative infinity. So I also need to make sure that it's going down. And then on the other side, I need to make sure it's going up. So I know that because I'm doing opposite behaviors, I'm creating an odd degree polynomial. Agree? So my odd degree polynomial, I'm going to keep it simple. I'm just going to do a little cubic for you. Okay, did I satisfy it? All right, do we feel confident in being able to read the limit notation then? Yes, perfect. All right, on to the next, just honing it in, make sure we're all there. Up next, it says, for a polynomial equation, it is easiest to find the end behavior of the right side first, okay? So we're going to put in this blank, right. The reason why it's easier to find the end behavior of the right side is because if we remember anything about our polynomial rules, our right side is determined by our leading coefficient. Do we remember that? Our right side is determined by our leading coefficient. So it goes to positive infinity if the leading coefficient is positive. Your heading, it goes to negative infinity if your leading coefficient is negative. Okay? Then, how do we determine the rest of the behavior? The rest of the behavior depends on whether it's an even or odd degree. Remember that? Okay? So, it goes in the same direction if we are a even degree on the left-hand side. It goes in the opposite direction as the right if the degree is odd. Okay, we should have left algebra 2 knowing that, right? Because Bob only had 4 dance moves, and it depended on if he was odd, even, or positive or negative, right? That's it. That's all he got. All right. So you should be able to also determine the end behavior without looking at a graph. All right. Because of those rules, we should be able to determine what's happening without looking at the graph. All right. So checking that we can, we're going to list out what's happening to the left and the right, and we're going to list out why are we saying these things. So we're looking for your leading coefficient. We're looking for your degree. Make sense? Okay. So the first thing we're going to do is state our leading coefficient and our degree here. So starting off here with A, our leading coefficient, is it positive or negative? Positive. So LC is positive. Our leading coefficient is positive. Our degree, is it odd or even? We have an odd degree. So we have a positive leading coefficient and an odd degree. Because we have a positive leading coefficient, we know that our right-hand side is going to positive infinity. Make sense? Because our degree is odd, we know that the left side is going to be doing the opposite behavior. So it'll be going to negative infinity. So that's all I want you to do is go through, identify whether the leading coefficient is positive or negative, and whether the degree is odd or even. Once you identify that, you're going to tell me what is the left side doing and what is the right side doing. Got it? Go. You can talk to each other, check with each other. Okay, on B, what is my left behavior? Positive, and my right behavior is positive. On C, my behavior is what? Negative infinity. My right behavior is? It is. On D, left behavior, positive infinity. And right behavior, negative infinity. E, positive left, right? Perfect. F, how we doing F? All right, let's talk about F. I was wondering. All right, so F, this goes back to paying attention to your multiplicities, okay? Your multiplicities tell you the degree of your function. So I have a multiplicity of 1, and a multiplicity of 1, and a multiplicity of 1. So the degree of this function is 3, which makes it odd, correct? Next, you're going to pay attention to your leading coefficients of each factor. My leading coefficient here is a positive 2, a positive 1, and a negative 1. So my leading coefficient is actually what? I have a positive times a negative. It's going to be a negative. So my leading coefficient is negative. So therefore, I have an odd degree in negative behavior. So my right side is negative, but my left side is positive. All right. Does that help? Remember, the multiplicities tell us what our degree is when we're in the factored form. Your multiplicity is the power of your factor. If there's no visible power, then your factor power is uno, 1. Casper the Friendly Ghost. All right. Yes. Cool. All right. On the next one, what we're going to do is the same thing, but this time we're going to actually write it in limit notation. Does it make sense? So we're doing the same thing, but we're writing our answers in limit notation. So up first, we're going to identify our degree. Our degree is the 4th degree, which makes it even. And then our leading coefficient is negative. I could have just written negative. Okay. Because of that, we know that what's taking place here? The limit as x goes to positive infinity, f of x is doing what? It's your right side, right? Your right side depends on your leading coefficient. And what was our leading coefficient? Negative infinity. So it's heading towards negative infinity. Okay. Your left side depends on whether it's odd or even. And because this is even, your left side is going to be doing an even behavior. Your limit as x goes to negative infinity, f of x is also going to head towards negative infinity. Okay. This is the end game here. This is the ultimate goal, is to be able to write it in limit notation. Okay. All right. So we're going to try it again here. Our degree, is it odd or even? Our degree is odd. Our leading coefficient, is it positive or negative? Positive. Remember, your leading coefficient tells you what your right side of your function is doing. So our limit as x goes to positive infinity, f of x is also going towards positive infinity. Make sense? Okay. Your left side depends on your degree. Because our degree is odd, we're going to be doing opposite behaviors. So our limit as x goes to negative infinity, f of x is going to be the opposite of our right, which makes it negative infinity. How you feel? Great? Doable? All right. The last piece is our technology piece, which is the graphing, doing it from graphing. Honestly, the other ones that you probably do need to do from the graphing are the rational models, right? The polynomial that you're given, should you be able to do this without a graph at this point? Yes. The only ones that I want you to do it in the graph are going to be your rational ones. Okay. So the rational ones, I want you to analyze the end behavior. Okay. By analyzing the end behavior, you're going to then just tell me again, what do you notice is happening with those rational functions? We're going to do it together, by the way. But I have to switch to the Desmos screen so I can do it. But that's what we're going to do. So before we go ahead, we're going to go ahead and push out our f of x for a. So for a, what is my limit doing? The limit as x goes to positive infinity, what is f of x doing? It's also going to, that's not an infinity symbol. How about say f of x is going to f of x? It's going to positive infinity. Okay. The limit as x goes to negative infinity, what is f of x doing? And why is it going to positive infinity? It's even. Even functions have even behaviors, right? Even functions have even behaviors. All right, so now we're going to graph these rational functions. How do I know they're rationals? Because I have a polynomial in the numerator and a polynomial in the denominator, okay? This is leading us into our 1B.7. So we're taking a little snapshot. And what this is going to show us is that just because you're going forever to the left and forever to the right does not always mean that your f of x is going towards infinity, okay? So that's the goal of analyzing these two functions. All right, so I'm going to go and open up my Desmos. So here was your practice that we were doing. Open my Desmos graphing. Ta-da! All right, we're going to put in our first function. Make sure when you're writing things in Desmos that you're either using f of x or y of x or identifying the name of your function. So I'm going to call it g of x because that's what it is. Make sure you're not capitalized also. I don't think it'll let me. In testing mode, we can't. Can I? F of x equals. And I need a fraction. So I'm going to start off as just, I'm old school with parentheses. So to me, it's just faster for me to do that and use forward slash, and then automatically I'll turn the rest into a fraction. I try to relatively ever open this little guy right here. I never open the keyboard. Can't tell you why. Don't know why. It's just something I don't ever do. Okay. So now here's our rational function. What we've learned about rational functions is that they have asymptotes, right? They have boundary lines that say you only can go so far. All right. So when we're looking at this function, as I'm going forever to the right, I'm not heading towards an infinity, am I? I'm heading towards a value. Do we see that? Same thing to the left. As I head forever to the left, I'm not heading towards infinity. I'm heading towards a specific value that I will never ever meet because asymptotes put you in the friend zone, right? You can get as close as you like, but you are stuck, buddy. You're there. Can't cross over, all right? So we have a couple ways of analyzing it. The reason why I say make sure you write it as either f of x or y of x is because we can analyze it by looking at the table, okay? So to get to the table, you click on the function, you click on the gear, and you're going to click on the table. This allows you to type in any number that you want. So like if I'm like, what's happening at negative 1,000? Well, at negative 1,000, it appears that I'm getting closer and closer to what value? To 2. Do we see that? Okay, what if it happened at 10,000? Still getting really close to 2. Okay, what happens at positive 1,000? At positive 1,000, looks like it's getting closer to 2. And I keep going. It's trying. It's trying. It's trying. And it's gonna show you that it is, but it never is. It's just that we ran out of space to do decimals, right? So you can analyze what's happening in this situation with a calculator, looking at the table and going from there. Does that make sense? So when we write our limit here, our limit is not going to be to infinity. Our limit is what we're approaching. And what are we trying to approach? 2. Does that make sense? All right, so let's go back so we can write it in limit form. Is it gonna pop up? There we go. All right, so on this one, change my pen color. Let's go with purple. So the limit as x goes to positive infinity, f of x is approaching positive 2, correct? And then the limit as x goes to negative infinity, f of x is also approaching positive 2. How we feel? Is that doable? All right, guess who's starting this? Try on the last rational. It's yours. Oh my God. Okay, so let's talk about it. So when you came over here and you did all your little fun stuff, I'm just going to modify instead of deleting, you know? No need to delete, just change. Go to the numerator, please. Thank you. So my numerator is now a negative 10, right? So we have negative 10. My denominator is now x squared. Shift 6 to make it x squared. And this is now what we're working with. All right? So when I'm looking at this graph, I can actually tell without looking at the table, correct? So as I'm going forever to the right, as x is increasing without bound, what is your y value doing? It's trying to get close to who? 0. And then as your x's are decreasing without bounds, what are your y values trying to do? Get close to 0. We agree? All right, perfect. So then when you write your limit should be the limit as x goes to, doesn't matter which one you write first, negative infinity, f of x equals 0. The limit as x goes to positive infinity, f of x is also equaling to 0. Ta-da! That's 1B.6. And that's all I have for you.